Kevin Kurtz, I'm the VP of Engineering for Quadrant Solutions. My group works with customers, PD engineers, quality control to design tests and permanent magnetic circuits. My story with Quadrant, I've been here for nearly 10 years. I was hired on as an applications engineer to try to help industrial customers design some larger equipment and learn some of the magnetics. At the time, I was doing a lot of quality control tests and things that weren't necessarily magnetic circuit design, and eventually moved into consumer electronics, helping them design these very small circuits and pushing the limit of what we can manufacture and design. My story with material engineering, did some university work with magnetics and surface degradation of very small magnets. The surface area to volume ratios of centered NdFeB magnets, there's some surface degradation, there's some damage that gets done, and we were studying that. Magnets have to be very small, they have large surface area to volume ratios. So all of this research actually helped out with our design and industrial work in that particular industry. Also, the medical industry uses really small magnets. There's a lot of textbook information and simulation design for larger magnets, but when you push the boundaries of how small you can get, it takes a really good fundamental understanding of what's happening in the materials. Challenging project I've worked on. Two immediately jump to mind. One's a good one and one's a bad one. So I had something really interesting we wanted to do. We kind of wanted to follow this signal design. We wanted to make the magnets work like this signal generation, and came up with this really cool idea. It was manufacturable. I really think it was going to work. Unfortunately, the project got canceled before it made it into mass manufacturing. But it was a lot of fun. It took a lot of work. It was one of the most interesting concepts I've had to work on. And it really challenged what we can do. The second one, they wanted to do something that was so strong and so out there. They had this rotational connection. And I don't know that it can be done with our current materials and the volume that they gave us. And I was an order of magnitude off. In magnetic circuits directly, the biggest factors are really design the whole circuit. This flux is flowing just like an electrical circuit. You've got to make sure you know the path that it's taking, where it's reconnecting, what's happening. I'd say watch the exponentials. The air gap, it falls off at an exponential rate for holding force. So if you can tweak that and get it closer, you're always going to have a more efficient circuit. Watch your flux density. That's at a factor of a square for holding force. So you want to make sure if you can do those. A lot of the other things are really linear. So if you can control those, you can keep things from having an overwhelming effect on the magnetic circuit. Motor design is challenging because there's a lot of factors that you have to look at, and most of them are going to be out of your control. So what is a motor? It's a tool. We want to move something, we want to spin something, we need a torque. So we're usually not looking at the motor itself initially. You're trying to fit this tool in your space and get this job done. So it's just a means to an end. So with that in mind, let's look at what we're trying to design. We want the outputs of this motor. We want the torque that's going. What kind of power curve or torque curve are we trying to look at on the outside of this? After we figured out what it is our goals are, we have to look at our inputs. What kind of power supply do you have available? What are we putting into it? Without knowing those things, we can't even start looking at windings or magnetics or anything else, because we have to have these outside design constraints that are within our control to try to look at them. After that, we do get a bunch of variables in the motor. How many teeth do we want? How many poles in the magnet? How many poles on the rotor? How many magnets are we going to need based on that? How many windings can we fit in there? Size, space, heat constraints, other things like that. But those are really secondary to the input and the output. A lot of EVs now are going to a brushless DC permanent magnet motor. So it's really not different from most of the DC magnet motors that you deal with. The difference is going to be like the size and the quality. The windings of the magnets are related. They have to have a certain distance between each other. You can easily demagnetize the magnets if you push on them too hard or have too large of an adverse magnetic field. You have a constraint on keeping the magnets magnetized with their own shape. You have a constraint on the coils. They're going to get hot. They've got a current flowing. You've got to fire them at the right time with the right position of the rotor to get it to push instead of pull, so to say. There are a lot of factors that go into it, but on the fundamentals, it's really simple. We've got two magnets, one's an electromagnet, one's a permanent magnet, pushing against each other. So the big things that are moving forward are, the first I'm going to say is cost savings. Of course, that applies to any product, but we can do that especially in permanent magnet motors because we're using this heavy rare earth material. It's very expensive. Neodymium's used a lot. That's 12-13% of the ore. So yeah, it's not as rare as it sounds, but we do need dysprosium and terbium and things that give these magnets coercivity, and they cost a whole lot more. There's only 1%, 0.3% of those inside the ore that we're coming out. So they actually are very rare and they're very expensive. So if we can try to eliminate those or push back on those. The second one I'm going to look at is really the quality control, the assurance that the motor's going to work. We're not engineering to cost down anymore. We're engineering for reliability, which is, you would think that would happen in a lot of industries, and it does. We have luxury brands, we have products that are better, but in EVs, it's really a concern. We want to use the best materials. We want to make sure that these are done properly. Understanding the fundamentals, understanding the physics of it, the materials is important. You can get away for a long time without that. You can do benchtop testing and trial and error, and that's really the difference between some mechanical engineer that doesn't understand the magnetic properties but just uses them, makes them work, form, fit, function. You're not always trying to cost down or using this on the brink of what we can manufacture. But my job is to make sure that if you are, we have support for that.